I couldn't resist. I'm trained in architecture. I worked in architecture for several years, but I've been speaking to mechanical engineers for the past 7 years. So I'm going to talk about functions and how it relates to form in an engineering context, in the context of nTop. Um, so I'm going to do a little bit of an intro on nTop and how it relates to functions, why functions matter, and ultimately how it affects an engineering workflow over time. So first, what is nTop? So nTop, for those who don't know, is an engineering ecosystem. It's a design software for making high complexity engineered parts, highly engineered parts with highly complex requirements. So think things like turbo machinery or engines, or like with many parts working in tandem with one another with um, a high degree of manufacturing precision. So nTop's also a design analysis environment, so you can evaluate the designs you're creating on the fly and augment your designs with the data that's coming from simulations. nTop's also a modeling tool. Quite simply, it's an implicit modeling tool that allows for direct interaction with geometry at kind of real-time interaction and super high complexity geometry. So this new type of geometry also requires a different type of visualization that most kind of CAD software today hasn't really had to confront. Implicit geometry is kind of a function in space, broadly speaking. There's really no discretization happening until you ask for it, until you are sending it to the machine or sending it to the renderer. So we developed a new rendering technology to display multi-scale geometry. So rendering on the fly, you can design high complexity shapes and forms in a really lightweight way. And you can also see them when you want to. You don't have to bog down your render or bog down your computer just to design something on the fly. nTop's also a functional programming language. It's a visual programming language, kind of like Grasshopper or Dynamo, but with a different flavor. Basically, we went with a kind of like Jupyter Notebooks vertical format that seemed to work more, is more aligned with how mechanical engineering software works, kind of like a model tree type software, but exposing this concept in a user-friendly way for this type of user base. This type of workflow is also self-documenting. So you work top to bottom, name your variables, comment. We think of nTop as a not just as a model that you're creating, but a document that kind of tracks the process along the way. So a little bit about the nTop technology stack. So it's really based in implicit modeling, which is we developed a solid modeling kernel, basically a completely new type of geometry, not a mesh, not a BREP, but implicit as a new thing. If you all are curious, Daniel Piker has a new plugin that released last month for this. Highly recommend checking it out. Fun stuff. But really, this type of geometry overcomes quite a lot of the CAD limitations with discretization and slow performance when dealing with high complexity things. Also field-driven design. So because implicits are just functions in space, anything else that's a function in space works with it. So let's say you have a simulation data set that's pressure applied in space. You can take that pressure function and use that to drive the geometric characteristics of your designs. And last, design automation, reusable procedural workflows to automate processes, save time, and scale engineering teams. I'm sure you all are familiar with that here. This is a pretty new concept in a lot of engineering workflows. So just taking this concept that like I've learned quite a lot about in the engineering or in the architecture field and applying it to engineering develops kind of new possibilities for this technology. So we work with a bunch of different companies, 400 companies-ish across aerospace, medical, automotive, industrial. Here we go. Okay, industrial and energy, consumer, and manufacturing and research. And there we go. Cool. So all this really matters. Or the kind of like implicit tag, design automation. Really, the reason this matters in engineering is that there's a lot of pressure to deliver products to market faster. Pretty simple use case. This is happening in industrial, aerospace, automotive. These are the types of parts that, when I say the word parts or assemblies, these are the types of assemblies that I'm talking about, like turbo machinery in industrial, like turbines in aerospace, and brackets and kind of structural components in automotive. So the bottleneck that we've identified at nTop is that really design iteration isn't fast enough. And in engineering, it's a pretty linear workflow where iterations happen and then there needs to be a revision. And it's almost like starting from scratch every single time, inching the way up to value rather than delivering value in a continuous way or an accelerated way, like in, let's say, software development. Um, each iteration is quite a lot of manual iteration. The traditional process simply doesn't scale if you're trying to bring products to market fast in high performance environments. So here's an example of a traditional tool. This is, I think, like Siemens NX, um, even more old school than Rhino, probably. These tools are surprisingly like rigid and really are difficult, even in a simple case where someone's trying to create structural ribs on something. Super fragile CAD operations, self-intersecting surfaces, like actually break this workflow and require you to remodel it. Even if you had a successful design edition, you need to start over if you're going to do another one. Also, complex parameterizations are difficult to construct. This looks like a really simple case. It's funny, like architects look at this and like, this would take me 5 minutes to model and whatever. But the reality is like, when you need high performance or high precision manufacturable models, this is really difficult to create. This could take more than a day, honestly, to construct this simple connection of curves and lines. And last but not least, complex physics are difficult to capture. Um, really, simulation tools are extremely decoupled from design tools in engineering today. Our goal at nTop is to start to blur that, blend that together, so you can use manufacturing data or simulation and manufacturing data to drive design. So some applications of where this is relevant at nTop are lightweighting, thermal management, fluid management, mass customization, energy absorption and comfort, acoustic and vibration, radio frequency. You'll see a lot of lattices and structural kind of things here. But like our main focus when we first founded nTop was developing like lattice structures, and there are definitely many more use cases in this. But you'll see like a lot of the places that we add value are like things that are really difficult to model in CAD systems. And it's used across the product development process. So from like a body design of an airplane to the structural design of an airplane, all the way down to the structural components of the detailed design. So a really specific example, drone fuselage, good kind of drone. Blue Flight is making products that are delivering emergency equipment in hard to reach places. So this is a really real application where the product performance affects saving someone's life. So every pound of weight actually means that they can carry another pound of rescue supplies. So weight really matters here. So we were able to reduction of this specific component, and there are many components on this that can be reduced by 25%. And also we're able to model it in a total of 4 hours from beginning to end, it's kind of funny. It's hard to believe, but this actually took 4 weeks for them to design this component using their traditional process. So and there are many parts on this and many opportunities to optimize throughout. So similar type of kind of aerospace related thing, like a thruster injector block for updating legacy systems for the Apollo era propulsion system, able to reduce 67% of the weight, decrease the cost, increase the thrust to weight ratio, and now they're producing 600 of these. So this is something that simply wasn't possible without nTop. Preaching to the choir, we talk about computational design all the time to engineers, and it's a new thing. And so I'm kind of excited to present to you all on this one. So here's a really like tangible example of what this means in engineering. Real equations that are used to design airfoils, for example. There's a known like official equation to create an airfoil. All of this can get compressed into simple UI elements in our software. So you don't have to draw the curves for this, like manually draw these curves for an airfoil to exist. So what that means is you can create all airfoils all at once, and test them. Pick the right one for the right use case by testing it with real data on the fly. So what this kind of looks like in practice is there are 3 major phases. So there's going to be the build phase where someone's building the computational model, someone's taking that equation and turning it into a model. There's the run phase, which there are many different flavors of this. This could be like automating. This could be just running once. This could be exploring a design set and picking one. This could be running an optimization. This could be training an ML model. But this is like running the same model in many different ways to find the best design. And the last one, nTop isn't really anything without good integrations into the engineering workflow. So um, it's important that we're connecting to existing traditional CAD tools, traditional CAE tools, traditional manufacturing tools. Even though we have a new type of geometry that's has all these benefits, if it doesn't connect to an existing workflow, it doesn't add value to the engineer's workflow. So we do this kind of through three kind of tools. We have nTop, which I'll talk mostly about, which is the implicit modeler, assigned distance field based computational model builder. nTop Automate, which is a deployable CLI to be able to run these automations and create plots and basically coordinate large data sets. And nTop Core, which is an SDK for partners to connect to our implicit workflows. All right. Now I'm going to talk a little bit about how nTop actually works. I think you'll find this a little bit interesting. Um, nTop literally is functions. It may not look like a function, but it changes the way you think about shapes in space. So instead of in architecture in Grasshopper and Rhino, in most CAD systems, shapes are actual physical objects with topology, with explicit things in space. Implicit basically means everything is in space all the time and there's a function, and that's all you know. So simple example of that is x equals 0. So where x equals 0 in an implicit equation is like, this is where the surface is. I kind of describe this as a graphing calculator to those who are kind of seeing implicit stuff for the first time. X can be anything. You can see like this gradient of values in space across kind of the radiating from the y-axis, but X is X. So really, when you want to find where the surface is, the render can find it on the fly. You can mesh it. You can turn it into a CAD surface. You can send that data generically to anything else. It really is just a function in space. Same with y. Y returns the x-axis. Y equals mx plus b, algebra 1. Here's a line. But as you'll see, it's not just a line. It's a line and all possible lines in this equation. Y equals x squared plus 2x quadratics, kind of like really functions are very, very simple foundational things that grow in complexity over time. You can combine them. You can, really, it's all about combining them in clever ways and getting the right level of abstraction. So a circle, for example, jumping from a function to geometry is actually a really simple leap. It's really like all geometry is in an implicit world is where the function equals 0. So x squared plus y squared minus r squared, there you have a circle. Where the kind of like blue interior of this model is like the inside and everything else is the outside. So negative values inside, positive values outside. The top of let's say a cylinder that I'm about to model is z equals 10, bottom is z equals negative 10. And by combining these functions and with maximum, for example, there you have a cylinder. So instead of saying, take a circle, make it a planar surface, extrude it, now you have all this topology, really what you're saying is, I have a cylinder function. It's like each thing is an object or kind of a function that can be stacked into the next. So same with trig. We do a lot of patterning. We do a lot of latticing, ribs, whatever. Really what we're talking about is repeating functions. So cosine, modulo, things like that. So y equals cosine x. If you want to apply that three-dimensionally, super simple example, you'll see gyroids all over our website and stuff like that. So cosine of x plus cosine of y. Now you have a pattern, a 2D pattern in space. By adding 3 together, cosine x, cosine y, cosine z, all of a sudden you have a structure. So really infill patterns, which you'll see quite a lot in 3D printing, metal additive manufacturing, or minimal surfaces and stuff like that. So all that really is just functions, wave synthesis in space. So turning that into a solid with infill is just saying or actually this shouldn't be min, that should be max pattern in cylinder. So all of that's a lot of math. This is, of course, abstracted in the software. We have functions that people think about from other pieces of software. So you have a cylinder function, you have a gyroid function, you intersect those and you get the same thing. So the kind of magic is finding the right level of abstraction so that users don't have to think about functions. They can just use them as objects and don't really have to worry about all the kind of like limitations of like where things will break in a CAD system. So as you'll see, this is also highly interactive. This is a real-time kind of screen capture of this. The function exists whether you see it or not. So the speed is really only limited at how fast you can see it. So this is like a real-time animation of if we, let's say we don't know what size the gyroid is, or we want this infill to be, we can drag it and see it live interact and decide when it's the right value. So the speed of the interaction actually like doesn't just increase the performance of the part, but it increases your kind of ability to evaluate what the right design actually is on the fly. So from forms to parts. So design exploration is extremely important, and we have a few different ways that we do that. So I showed a bunch of cylinders and gyroids and nonsense. This is a real example of a real part, kind of an impeller part that's in a turbo machinery assembly. It has very real performance requirements to be able to kind of like pressurize fluids basically in a vessel. And the function is very known. There really aren't that many parameters. I mean, this looks like a lot of parameters, but this is the entire part design can be captured in a very closed set of parameters, which means like not only can you change the values and see it update live and whatever, but you can actually measure the output of that. So with simulation in the loop, you can capture all design possibilities for all parameters all at once in a really fast, real way without having to worry about it breaking. An implicit function is always going to return something. It might not be the right thing or like the best thing, but you'll know right away. It's not going to break your automation. So which means you can use this data for like a design of experiments. If you don't know if the parameter should be 1 or 3, you can run 1,000 iterations in a few minutes and find out. If you want to train an ML model to figure out, make a tool to design the best impellers depending on your situation, you can generate huge data sets without having to worry about the gaps in your data set in between. And last but not least, design exploration through interaction. Because you can generate implicit models on the fly, you can, in this example, generate a texture on a panel. And basically, by interacting with it live, you can see where it's manufacturable. You can see where the texture is and isn't, where you might have problems with manufacturing or kind of producing this part. And last, parts are nothing without the ecosystem. So we're working on integrations with PLM solutions, so nTop can coexist with the engineering ecosystem as a whole. And we're doing this through kind of nTop Connect SDK, where we're partnering with Cloudfluid and Tech Solutions, developing better interoperability with CAD systems. So here's an example of Autodesk Fusion, CFD tools and CAM tools, and of course, making sure that our implicit files are compatible with legacy CAD systems. So here's a really good example of how we're working with Intact Solutions. So it's talking a bit about like integrated simulation, and if you're talking about implicits, which are a new type of geometry, really you need a new type of simulation. So we can mesh and we can always send to an FEA, but the value of nTop is getting feedback on the fly about your design. So we're working with Intact to do real-time simulation results without having to mesh, without having to work with discrete geometry. Same with Cloudfluid, good example of sending like an nTop model with no discretization, no meshing into a fluid engine. And this is used for like heat exchangers and kind of like that type of machinery in an assembly. Also working with Hexagon, kind of the same type of thing with simulation, meshless CFD. Materialize, so the part's nothing unless you can manufacture it. Here's a good example. This doesn't do it justice. These parts are huge. These are like several feet big. So these types of parts are extremely difficult to mesh. It could take gigabytes, or maybe it's not even possible to mesh these things, but sending this into a metal additive manufacturing workflow with implicit interoperability is essential to getting these parts made. And last but not least, my favorite, Autodesk Fusion, bring it into design tools that people are familiar with. So by pushing on the kind of like technical limitations of existing CAD workflows, we're actually shifting the industry forward to be able to support CAD implicit models themselves. So driving change in the industry, really, the way to do that is to deeply embed yourself into existing engineering workflows and kind of push where traditional softwares didn't think were possible. So, and yeah, that's it. Thanks.